Hello everyone. Welcome to ACSL class. Today's topic is digital electronics. So to understand digital electronics, we need to remember how to do bit string flickering. We need to do Boolean algebra, and then we'll introduce you to digital electronics and the more advanced concepts inside. So the main things you need to know for bit string flickering are what not and or and XOR do, or exclusive OR. So not just turn something into its opposite, and it's only true if all the elements in it are true, or is true as long as at least one of the elements is true, and XOR or exclusive OR is true only if we're given two elements, they differ. But there is no saying for three unless because for XOR for three we have to do A XOR B and then XOR C. That's how we would do it with three. So some things you need to know are the commutative law, which basically means or if you have two different terms that are separate, the order that they're arranged doesn't matter. Like x plus y equals y plus x and x times y equals y times x, which is similar to addition and multiplication. And then also associative law that grouping parentheses or regrouping the terms in an expression doesn't change the value, such as like if we did x plus y and then plus z would be the same as x plus of the sum of y and z. And the same thing with like multiplication, like x of y and z is the same as x and y multiplied by z. And idempotent law just means if anything is ORed or ANDed by itself, it is equal to itself. If this doesn't make sense, if x is false, false and false is still false. If x is true, true and true is still true. Sorry, true or true is still true. And then if it's ANDed, if false, false and false is still false, and true is still true. Annihilator law is basically you can just replace something with a true or a false. Like, because if we did a variable or true, no matter what the variable is, they will always get true. So then you can just replace the variable or true with just true. And if you did a variable and false, no matter what the variable is, it'll always return false, which is then you can replace the variable or false, variable and false with false. And the identity law basically means if a variable or 0, that always gives you the variable. Since adding a variable or false is like just not having that or term at all. And the variable and itself will always equal that term because anding something, anding a true is the output is still only true if x is true. So if x was true, then x and 1 is true. If x is false, x and 1 is false, which means x just stays the same if you do and 1. And then the complement law is when we take x and we or and it with not x. So in the case where if we're doing or x or not x is always equal to 1 because no matter what, one of them will be true and one of them will be false. And true or false will give you true at all times. And then the same idea applies to the complement law for and, in which if you do x and not x, no matter what, you will get false because one of them will always be true and one will always be false. And true and false will always give you false. Does anyone have any questions? And then some more fundamental identities is if we have the absorptive law, like we can absorb like terms through either if we have like x plus xy, it'll always equal to x. So x or xy will always equal to x. Because even if we drew out the table 1 0 0 1 0 0 and 1 1, if x this is x and y, x or xy this is 1, this is 0, this is 0, and this is 1. And looking at the outputs, these terms always match, so this law is true. And then x of x plus y is always equal to x. Because if x is false, we know that this is going to be false. Because false and anything, it gives you false. But if x is true, then the inside of the statement is also going to be true, which means true and true is still going to get x and true. It's still going to be true. So if x is true, this statement's true. If x is false, this statement's false. And then the distributive law basically just means we're allowed to factor out or more by an expression like x times of y plus z is the same as xy plus xz. And then De Morgan's law. So in negative of a or expression, which we will learn at which could be nor, or can be expressed as not x, not y, with the separation saying that it's not just the not of x, y. And the opposite applies to if we have a NAND, not and, where not x, not y, sorry, not x, y will always give you not x plus not y. Okay, and then double negation is basically if you take the negation of a term, you always just get the original term. Since this a way of thinking about it is we can make this negative, and the negative times the negative always gives you a positive. And then XOR and XNOR or XNOR, they're basically opposites, where XOR is the opposite of XNOR, which basically since XNOR is true whenever the terms are the same, and XOR is only true when the two terms are different. So basically a digital electronic is a digital circuit that's connected from like logic gates. And usually we send information through a computer using wires, and that we send informations in ones and zeros. And then computers use these logic gates to transform the ones and zeros from the input and then put it out into an output. And then a logic gate is basically a device that performs a Boolean function, which basically is a logical operation that performs on some inputs that produces a single output. Basically, you accept inputs and then outputs a result on their state. So some of the simplest logic gates are the buffer and not, where if we just have a buffer, it just outputs whatever you put in. So if it was false, if it was 0, it would output 0. If it was 1, it would output 1. And then the other one, not, is just represented by either a line above the number, above the letter, which is usually how it will be seen, or this symbol here. And basically, it just flips the function. If you had false, which is 0, it would return 1, which is true. If you had if you put true, then you would get false as an output. Okay, and then some other ones you need to know are and, which basically just means you take the two inputs, and you only return true if both are true, which is represented either by just two letters next to each other, or a letter and then a multiplication dot and then another letter. And then NAND or NAND is basically not of not of AB, and or shown as a not of A dot and then B. And this basically returns true as long as both values are not 1, since and returned it if only both values are 1, everything else was 0. And not of 0 is 1, so everything else except if both were 1 would be 1. And if both were 1, since and originally returned 1, we would have to take the not of that, which is 0. And then OR is just A plus B, which just means as long as A and B are not both 0, or just in other words, A or B, at least one of them is 1, the output is 1, which is represented by a plus. And NOR is A times B. It's just, sorry, NOR is just the opposite of OR, which is basically represented by a line of A plus B, which basically only returns true if both are 0. Otherwise, it returns false. And then the two slightly more complicated ones are XOR and XNOR, which basically just means you're taking XOR, or exclusive OR, only returns true if both are if the outputs are opposite from each other. Another way of representing this could be not A B or not B A. This, since if the are opposite, this would return true and this will return true. If they're the same, none of them will return true. You'll need to keep this in mind. This is important identity for later. And then XNOR just means as long as they're the same, then I return true. If they are not the same, then it returns false. So basically that just means either not A, not B, or A, B. At least one of these will return true at all times. Sorry, and about this one, only at least one of them will return true at all times. Because if both of them are false, this will return true. If both of them are true, this will return true. And for XOR, if A was false and B was true, this will return true. Otherwise, the second one will return true. Okay, so first practice. So we have this small circuit, A, B, C. And we need to make the circuit false. And this is a NAND, and this is an OR. So just we need to see how many triplets A, B, C make the following circuit false. So please try the question. Okay. So you guys have all been giving me the answer of 110. No, where it just said find all ordered triplets. It did not ask how many. But in most of the time, in actual ACSL questions, it will ask you how, it will actually expect an answer of how many, not giving you giving a triplet. But the answer is just 110, since NAND returns false only if A and B are both 1. So this so these two have to be 1 because this is an OR. And so this has to be 0 and 0 in order for the output to be false. Which means that, and since this is OR and we have 1 0, the other must also be in 0 for it to return false, so C must be 0. Okay. Bit more difficult problem. So we have A, B, C, D. And we need to see how many A, B, C, D tuples return true. And so this is not, this is and, this is not, nor, nor. So please try this as well. Nor is just not of or. Not. Sorry, I just realized I went back the slide on accident. Wait, no, I here. Uh, the most efficient, since this is not actually simplifiable, if you were to simplify, you would get think not AC plus not sorry not if you were to simplify, and then plus not A B not C D not C not D, which if you were to apply as many expressions as you could, any rules just cancel it out, you couldn't. So the way to do this would be to just the way to do this would just be to list out every single A, B, C, D tuple, which you would only have 16 of, and sure. Yeah, I know. Switching screens. But if you were to list out every single A, B, C, D, where where this is the problem and this was P, this was Q, this was R, this was S, and this was T. Basically, if you were to list every single one out, you would see that there was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values that there are 10 values that 10 tuples of A, B, C, D that when they are listed out, when you finally evaluate the entire thing, you get an answer of output of 1 from T, which is the ending output of a circuit. Um, okay, next problem is, so we're given this Boolean expression and we need to simplify it. Basically just get an output that's as simplified as possible. And this is or, this is not, this is nor, this is and this is and. Okay, so a couple, you guys have been all getting this correct, but basically we're given this as A plus B. And this is not A of A plus B, which would give you not A plus not A B. And since this is always going to be false, so we can always remove that. So then this expression here will just eventually be not A, B. And then here is not B plus C, which using De Morgan's law would give you not B, not C. And then the final output would just be A, not A, B, not B, not C. And B, not B, always gives you false. So no matter what you put at A and C as, you always get false. So the output would just be 0. Does anyone have any questions? Not, let's move on. We're given this Boolean expression, and we are asked to simplify it as much as possible. Okay. Uh, so we know that this shape here is just AB, and this is A plus AB, which can be simplified to just not A. Sorry, A. And then we have B here. So it's just not A or B, not of A or B. And some of the answers I saw were just this, but we can still simplify this further. Using De Morgan's law, this is just not A and not B. And that's just their answer, not A and not B. Okay. And then so we have this digital circuit here. And they invented a new circuit logic gate in which this rectangle here and is true if exactly two of the three inputs are true. And we are asked how many order triples make the digital circuit true. Okay, so this problem is able to be reverse engineered, in which, so we know that this has to be true, which gives us exactly three cases. One is true, false. One is true, true, and one is false, true. And when I mean like true, false, true, true, false, true, I mean for these two. These two give us that. So the first case where this is true and the second one is false means that A, B has to be true and C is false. So that gives us 1. So 1, 1, 0 is 1. The case where it's true and true means these two have to be true and B has to be false. So that's 1, 0, 1. And the third case where this output's true is false, true, which means A has to be false and these two have to be true. And that just gives us a total of 3. Okay. Uh, so we have a Boolean expression here, and we need to simplify it as much as possible. Okay. Basically, we have a and not of man. Basically, not of and, which is not a b, which using De Morgan's law gives us not a plus not b. And then we add c to the mix, not a plus not b plus c. And we have a plus not a plus not b plus c. And a and not a, no matter what the other values are, will give you true. So this output is just true. And when we take the NOR of true and C, its NOR of true and C will give you not C false. And anything and false always results in false. So the output is just false or 0. Okay. We have this Boolean circuit, and we need to simplify it. Okay. So to simplify this problem, we first evaluate this as not a B, and then this as A plus not a B, not A, and then just normal B, which is not simplifiable yet. And then we get of the A plus not a B with B and then not. And using De Morgan's law, we get this as not of A plus not a B and not B. And then using De Morgan's law again, we have this as not A, not of not A, and then not of B, which this part plus not of B. And this part simplifies to not A, not B, plus not B. And then you can either cancel this term out because it's not A, or you can say this is not B, so then these two merge. But whichever you do, your final answer is this term's going to be eventually be gone, and you're going to get not B. That's your entire answer. Okay, that's going to be all for today as we are out of time. Does anyone have any questions? Uh, if not, then you guys can leave.